आज would be a final session on AI/ML rack. अगर कुछ डेमो वगैरह बचा तभी वो रहेगा, otherwise we will move on to other core architectural, core system side from this, right? So maybe this is the last session on vector databases, right? So today I'll just go through what are the fundamentals on vector databases, how vector databases are, let's say, different from the traditional databases that we all know about it, we have all used it, right? NoSQL, SQL databases, say how vector databases are different, right? So those things, then we will go to bullets when I mentioned नहीं किया, so I'll just quickly go through this. So we will go through embeddings, just touch upon because ये सब हमने cover किया हुआ है पहले से, vector और embeddings क्या होते हैं. Then we'll go through distance metrics, मतलब how do you calculate, what is your, how do you calculate, how do you basically search, right? What is your criteria to search inside vector database? Then we will look at different ways, cosine similarity या फिर equality and distance, ये सारी चीजें. Then we will go through the nearest neighbor, ANN, and ANN, why ANN is done instead of NN, right? We will look at majorly 2 or 3 different ways of doing a vector search. What are doing a vector index, right? So what are the different vector indexes? So primarily production ready, I think there is only one which is production ready largely, right? 90% of the cases is HNSW itself. But we'll also look at maybe how we evolved to HNSW. So we'll look at some other different indexes also, which came maybe before HNSW. I'm not sure on the order, but maybe those are not optimized, so folks move to HNSW. HNSW ko thoda sa we will see in detail. So the HNSW is basically the core of today's discussion. And HNSW mein we will see that how we evolved into HNSW, then what happens in HNSW when you construct the graph, then when you try to search the graph, and the parameters of HNSW, M, EF, EFS, and EF construction and EF search, both the HNSW parameters we will look into. And then thoda sa we will just go through, because these are all indexes only we talked about. So we'll also cover what are the database aspect of, right? So which is the database management side of it. And then how some of the database, prominent databases like Milvus, Quadrant, Pinecore, or Vespa might be doing some of the things internally a little differently. So that we will touch upon. And then these are the core aspects of any database, right? You want to know about how whether it's consistent or strongly or eventually consistent, durability, sharding, multi-tenancy. Yes, all these things we will just quickly see that how vector might be managing these things compared to, let's say, the normal databases. And then hybrid, little bit touch upon hybrid, that how hybrid is different from how a vector database might be evolving into a hybrid database, which is supporting both lexical and semantic use cases. Then thoda sa we will look into memory versus disk, where does these indexes gets created and all. Yeah. So this is the agenda today. Yeah. So any questions like before I start, right? Or any comment on this, right? It's really important to connect two universes because this is very different universe.
So, I mean, in the LLM, where do we use that? I mean, just to make sure that.
Yeah, so Dheeraj, good question, right? So, abhi jaise first we saw the RAG example, right?
Yeah.
So RAG mein what we were doing, we were using the natural language capability of LLM to basically to given a context and give parse the user request and explain and articulate. Ye sab capability LLM ki hai, right? Which we are using. But LLM always wanted a context, right? Now that context was something which you can pull only from vector database, right? I mean, you can pull from other sources also, but we were using vector database there. So finally, vector database आपको क्या करेगा? आपको capability देगा. It will give you an ability to search vectors, right? Any database, what capability it gives you? It just gives you an capability to search through things, right?
So say my company, I mean, works with the VDI, right? So so all the context from the VDI space, I will provide as a vector database to the my LLM application.
Yes.
So LLM will be converting the user input to some format, and then we will use that token or something and then search it in the vector database.
हाँ, आई थिंक ठीक है, मैं इसी से स्टार्ट करता हूँ. आई थिंक तुमने अच्छा क्वेश्चन पूछा, जस्ट टू कनेक्ट डॉट, बिकॉज आई वाज आई मीन आई हैड दिस अंडरस्टैंडिंग, सो आई कुड नॉट कम टू दिस, राइट. सो पहले ये देखते हैं, मतलब ई कॉमर्स एग्जांपल लेते हैं, राइट. दैट्स द इजीएस्ट वे टू रिलेट टू, राइट. So e-commerce में, let's say you are browsing on Flipkart, Amazon, Myntra, right? So what you are looking for, you want. So let's say you went to the search page and you said, give me a. You will say, I want a running Puma shoe, right? Puma shoe running, ऐसे कुछ you search, right? For running, or a party wear casual shoe, something like that. Any kind of queries you put, right? या मुझे कुछ घर के लिए कुछ प्रोडक्ट चाहिए. Now, so अभी तक all of these is certified. This is the whatever result that you get is mostly from a lexical search, and underlying layer में lexical search हो रहा होगा. What it will do is it will just try to do a matching, word based matching on that, right? And word based matching करके आपको result देगा. But vector database में क्या होगा कि now you will say that I will convert this to a query, this query which the user has given, sorry, I will convert this to a vector, right? सो एम्बेडिंग जनरेशन देखा था, राइट, तुमने, जैसे वर्ड टू वेक और ये सब जो हमने देखा था, राइट, यू वर पार्ट ऑफ दैट. सो यू विल जस्ट टेक दिस सेंटेंस, इट्स जस्ट अ सेंटेंस क्वेरी, द सेंटेंस दैट यूजर हैज गिवन, यू विल कन्वर्ट इट टू एन एम्बेडिंग. नाउ दिस एम्बेडिंग, नाउ यू गिव इट, यू सर्च इन द प्रोडक्ट स्पेस, पूरा प्रोडक्ट का भी वेक्टर बना लो, and then put it into the product vector space, and then put this query also in the product vector space, and then try to look for which query is similar to this query vector, which product vector is similar to the query vector, and then you return the result.
Okay.
Right? So purely search का तो यही use case है. Now this can be used in for RAG use case, या फिर MCP में use कर लो, agentic में use कर लो, right? कहीं पे भी use कर सकते हो, but purely this is the core of this, right? What is important is that you use the same text embedding to transform this query vector into a query vector, and then products also you would have used the same text embedding to transform into the embedding vector, and then only these are both are on the same vector space, right? Then only you will be able to do a cosine similarity, for example, right? And say that अगर shoe का query है, तो shoe का query is more near to a running shoe or a casual shoe than a shirt query, right? Than a shirt product, right? For example, so that's the reason you will be able to return a shoe. Right? So this is the pure sweet spot जहाँ पे ये use होगा, right? This is the core use case for vector database. ठीक है. Now we'll I mean, having set the context, we will proceed with just again with some basics, right? So vector versus traditional database. So vector databases में what we do is we will be storing embeddings, right? Now let's say आपको दो image search करना है, whether let's say one. So let's say you have a vector database for all the animal images, right? Cat images हैं, dog images हैं, और human beings, mammals, सबके images हैं उसमें. Now what you can do is you can give an image as a vector. So you take any image, let's say maybe it's a human being image, right? You convert it to a vector, and that vector again you put it to vector database, this animal vector database. So it will be able to match human beings more than it matches. So it will be more similar to the human beings, and it will be able to give you ID for that image, human के जो आपके जो documents होंगे उनके, it will give you the links, right? Return that links instead of that, right? So there also you can put, so you can convert images, audio, text, your audio, anything, you can take it, convert it to a vector, and that you put it into the vector database, and then you can do a search on in a similar fashion. So whatever is your query could again be an image, or it could be a text or audio. Only thing is that you use the same embedding transformation model, convert it to a text embedding, and then search in that space, right? I hope this is making sense, right? ठीक है. So this is kind of unstructured because there is no, it's not like a जैसे SQL में होता है, right? That you have an ID and then employee is there, department is there, salary is there, right? So it's pretty structured that in that sense, all the information in one row are like related to that person, that object, right? So in that sense, it is just an high dimension, very high dimensional vector. That's the reason it's being called as unstructured. And this place it was very, very structured, right? So this is the difference in the data type of both of these. Search method, this is very important to understand that in vector databases, you can never search exacts, right? it always does a similarity search, right? That okay, because vector database में कभी भी आपको there is no result which will not match. Potentially every result which is there. Let's say आपको अगर हम product database की बात कर रहे हैं, e-commerce product database की, and that there are 1 million results, then all 1 million will match any query that you fire, right? Right? Let's say you only have database for home decor products, but if you search with shoe vector, then also home decor products will match shoe vector, right? Its only thing is, let's say अगर कोई उसमें home decor का product रहेगा, तो that is more closer to the query vector, and then other shoe vectors will be more distant to it. That's the only difference. But otherwise, there is nothing like, because you are not doing any kind of an exact match. Exact match is not possible. You are only doing a similarity. Similarity search is the only way you can identify, right? So this is the only operation which is potentially done on a vector database, just looking for a similarity compared to the query embedding, right? इन सब डेटाबेस में हम क्या करते हैं, राइट? जैसे SQL या NoSQL डेटाबेसेस में what we will do is we do an exact match. So we take the query and then we parse the query, or take whatever we do, right? In the inside, maybe these are the kind of indexes we will use, right? If it's a MySQL, a MongoDB, or it's like a key value store, then we might be using hashes, or it might be a document store like Lucene Base, Solar, OpenSearch, Elasticsearch, and we might be doing an inverted index search. But we are always doing an exact match there, right? In case of vector, you will only be doing a similarity match. यहाँ पे एक और important है that similarity match, that this is similarity match is actually a knowledge that you have stored, right? So you are doing a knowledge search. So, but in case of in here, it's a very dumb search, right? In case of non-vector databases, it's a dumb search. It's just trying to see कि यार ये text keyword या ये text जो user ने दिया है, whether it is present in my database or not somewhere, right? So it's very dumb in that sense. But vector databases में it's very it's a knowledge that it has created within its boundary, right? And then it's trying to do search similar knowledge. It's trying to find a similar knowledge, right? So this distinction is very important. I hope I think everybody keeps this in mind, right? So यहाँ पे क्या होगा कि आपने जैसे वो एप्पल वाला एग्जांपल था, राइट? जैसे Apple being a brand, and Apple, how many calories are there in Apple being a fruit, right? So if you search in these databases, right, it cannot distinguish between both. It will just search for Apple as a keyword there, right? And then it will just try to split the text, and then will do a text-based matches here, right? So यहाँ पे it's a very dumb. It cannot distinguishes based on the context, right? But vector database में आप search करोगे तो query embedding for vector as a brand and vector as a fruit are very, very different, right? So this will match based on the context. If you are looking for a brand, it will match the Apple as a company. If you are looking for a fruit, it will match only fruit. So this is, in that sense, it's able to encode that knowledge and then search within the knowledge space. But this is like a dumb, it will just try to do a kind of a text-based match. So no intelligence or no knowledge is there, right? Okay. Dimensionality, right? So this is important. So traditional databases handle dozens of columns, and vector database handle thousands of dimensions. So this is, I think, pretty clear. No need to explain. We have seen that vector databases, you can the higher the number of dimensions, the more rich understanding it can encode, and then better will be your searching that you will do, right? So जैसे अभी कोई text embedding का हमने example लिया था, तो that was 384 dimensions that was encoded there. Then if you go higher, right, then you can maybe 768 dimension hota hai. Then you can maybe go more than 1000, right? So the higher the dimensions you will go, the better will be your search quality will be the best, and more knowledge you are able to take more knowledge and then encode into a vector. But I think this is very important, that performance will degrade very sharply if you go with very, very high dimension of embeddings, right? Just think of, let's say आपने अगर 384 or 768 dimensions के दो embeddings लिए, right? So the size of embeddings, right? So when you are saying 360, 384, then there are 384 floating values in an array, right? And then you have to, any dot product that you are doing, or you are transferring this embedding over a wire, over a network, and then 786 आप कर रहे हो, तो it's like a huge amount of processing that you will be doing. So both in terms of bandwidth transfer which happens over the network, in terms of the compute that CPU will have to do जब आप core processing करोगे, all of that will be much higher when you go for a higher dimension. It's not very मतलब it's not incremental, it becomes very high, right? जैसे आप एक float है उसके बाद दो float ले लोगे तो maybe you will not even notice that even at a very 1 million kind of an RPM. But यहाँ पे if you have that kind of an RPM, it's a huge difference. The hardware you will have to throw, the compute you will have to throw will be very different, and then you will need much more hardware to be thrown even to achieve that kind of performance in terms of latency and throughput, right? So just since we have touched upon latency and throughput, I'll just there are two aspects to this. So latency is, let's say, now this e-commerce search that we talked about, right? And then you have a query vector, and that you are matching to that, right? Now to get a latency of, let's say, within 50 ms or 100 ms, you'll have to really optimize अगर आपका scale बहुत ज़्यादा है तो, right? That how can you do a match, and then we will look at different kind of HNSW index and other indexes, that how these indexes will help you achieve this read latency. And then throughput, I mean the right throughput, right? Because now let's say that there would be an update on that product, right? Some metadata of that product gets changed. Because of that, the embedding of the product will change, right? Let's say आपने embedding बनाया है, उसके title, description, brand, article type, category, मतलब किसका प्रोडक्ट है, किस कैटेगरी का प्रोडक्ट है, वगैरह वगैरह यूज करके आपने एम्बेडिंग बनाया है, राइट? उसका तो अब आपने जब इन सब चीजों को यूज करके एम्बेडिंग बनाया है, तो so when let's say some of these attributes changes, right, then you will have to also go and update that inside the vector database, right? So it will go and update some index and some attributes. So all of these also you will have to see that, okay, what is the kind of throughput I can send to that vector database, right? Will it scale to 10k RPM, 20k RPM, or 50k or 100k RPM support कर पाएगा नहीं कर पाएगा, right? So these are the two things which will become really constrained. Maybe in some databases में भी होता है ये, right? We always talk about that MySQL is maybe read optimized and it's not write optimized. But let's say an LSM based databases like which uses Solar or Aerospike, which use LSM tree inside, some form of LSM tree, those, or Cassandra, right? These are more write optimized because उसमें आप faster write कर सकते हो, इसमें आप faster write नहीं कर सकते. But those will not support read, right? So similar constraints are there, and in fact these are much more important now in case of vector database. And then you will see कि आपको एक ही, अगर let's say 1 million products हैं आपके e-commerce में, तो उसका अगर आप उसका vector database बनाते हो तो आपका hardware footprint much more होगा to support a similar kind of NFR for the user in terms of read and write. And then अगर आप उसका ये बनाते हो, उसका ट्रेडिशनल डेटाबेसेस नो सीक्वल सीक्वल बनाते हो, तो आपका हार्डवेयर फुटप्रिंट जो है वो काफी कम रहेगा, जनरली स्पीकिंग, राइट? बट ऑफ कोर्स वी विल हैव टू सी दिस. ठीक है, सो मूविंग ऑन टू एनी क्वेश्चंस हियर? Okay, so I'll move to this. This is a, अब ये वाला एक चीज देख लेते हैं. So this is important, right? So we can see, we can maybe look at, these are the traditional indexes, right? In maybe MongoDB, MySQL, we support these B or B plus tree index. अब इसमें क्या होता है कि so what we can do is we can convert an order in problem into a log in problem very easily, right? Order in problem, why I'm saying order in problem is because traditionally अगर कोई मैं optimization ना करूं, so essentially जो भी query आएगी, I'll have to go and match with each of the records, right? So that's like an order in problem, order in time complexity I will get, because I have to, whether this should be part of my result set or not, I will only get after I match with all of them. That's like an order in, right? But what we do is, in case of let's say MySQL or these days, what we rely on some property of one of the attributes, right? Let's say uska koi bhi primary key, for example, if I take, right? So, and the query is on primary key. I'm on this query, right? So I will see that there is a inherent cardinality in that primary key, right? So it's like it's a number. A number is one dimensional only. So I can say that I can safely, when I'm searching, I can, at every step, I can ignore half of the space, right? So this is my entire search space for, let's say, search, right? मेरे पूरे documents इस search space में है. So now I come and I see that whether it is less than 30, more than 60, or it is between them, right? And based on that, at each step, I am, let's say, able to ignore one third or two third of the result set, and then I can only search on a part of one third and two third, right? So this is helping me narrow down the entire search space drastically at each space, and that is the reason maybe I can achieve a log of n time complexity. Let's say in these cases, right? This is even much better. But same you cannot do in case of vector database, right? क्योंकि vector databases में there is nothing like one dimensional ordering जैसे आपको मिल जा रही है यहाँ पे, right? So these are, because of the numerical ordering, you are able to say that okay, I don't need to go to the right side, I can only go to the left side. So पूरा ये right side का tree जो है, that is you're saved. You don't have to do a comparison here, right? So that kind of understanding you will not get in a vector database, because it's a very high dimensional, and there is no cardinality on one of the attributes, right? So this is the problem. This is called as like this is the gap, major gap, and this is called as a curse of high dimensionality, right? So this, we will see that okay, what are the kind of indexes which can be supported in HNSW index, right? I hope this is clear, right? This indexing part.
Yeah, sure.
Okay, sir. Okay, so we'll go to the core fundamentals, which is embedding. So I'll again not cover this because this we have covered in detail when we were discussing this, right? So vector and embedding, we saw about king and queen, and then how king minus queen plus man. नहीं ऐसा कुछ था ना जिसमें it became equal to woman, right? Where royalty was there. So this is the embedding representation which we will do in some vector days, right? And embedding models, जैसे ये वाले. So last time I think we used also one of the text embedding models from Hugging Face. There is a yeah, हाँ जी. So similarly, अभी जो embedding models है, so these are the different kind of text embedding models. So it's important that हम ये समझें कि this we are talking about text embedding models here. So transformer का जो पहला part था, right, which basically does an encoding, and then so BERT is like a sentence transformer model, so that can be used, or E5 can be used, right? Any kind of text embedding model has to be used so that it gives you. So this is typically what is happening, right? We have a data and then we convert it to embedding. So these are the embeddings, right? It will always be between -1 to 1. And then, so this is like one embedding, right? So you have one value, second value, third value, and this is 1, 2, 3, 4, 5, 6, 7, 8, maybe 15 or 15 dimension का ये embedding है आपका. Yeah, and then vector space we already have seen. So whatever, let's say, this is kind of a space where you will be searching. So this is, let's say, about fruits or different type of things are there. Maybe for product, again, you can have a similar kind of space where all your products are there, and then query vector, you will have to match that where my query vector is, and then how does it relate to those products, right? So ये जैसे आप देख सकते हैं यहाँ पे boat and ship are this side, all the fruits are this side, and then yeah, these sports things are below, right? This is like an entire vector space, and then we'll have to search in that vector space, right? एक बार distance matrix where we can focus. So there could be, one is cosine similarity. I think we have talked enough about this, right? So this is like two things are there, and then whatever is the cos theta between them, that is the similarity between these two, right? So that is how you calculate whether two things are more similar to each other than other two things. When other thing is here, then the cos theta will be higher, so that will be less similar. Other thing is, of course, Euclidean distance. This also we know that this is the basic distance formula that we have read, right? So this is another way to compute distance between two vectors, and this can also be used. But इसके साथ problem ये होता है कि again, when you take the dimensionality, this is like a two-dimensional, right? If we take it to, let's say, 384 dimension or 786 dimension which I talked about. Most of the vectors, मतलब जो distance होता है among them, that becomes very close enough, right? It's not like one place the distance is very large and one place the distance is very small. So that kind of problem comes when we take it to very high dimension Euclidean distance को. And then other thing is इसकी जो value होती है, that's not normalized between 0 and 1. This value can be any arbitrary number here, right? So because of these reasons, I think cosine similarity is something which has become a standard to search in the vector database. Others is a dot product. So dot product आप देखोगे कि dot product लो या cosine similarity लो, it gives you always the same. It's the same thing, right? So अब cos theta is nothing but this. So you do a dot product of vector, then you divide it by the absolute this. Even if you don't divide it by absolute this is also the same thing that you will get by multiplying both the vectors, or matrix multiplication when you do for both the vectors. So dot product and cosine similarity will give you the same result. Okay. I'll go to the indexing strategies now. So indexing strategy में so one typical indexing strategy could be let's say आपको vectors को index करना है, right? So maybe if we will start with this, it will make sense more. Yeah. So let's say this blue one is the query vector, and then this yellow one is all the candidates which we have to match, or maybe product in our e-commerce example. So now there is a blue vector and then this vector, and how will you basically create an index, right? That is the problem we are looking for. So let's say हम बोलते हैं कि we will just have one plane index only. I'm not going to multiple planes here. So how will I calculate the distance? This is the distance between two vectors which I am looking for, right? Let's say if there are two candidates, now this is there, I'll see that which one is more similar to each other. Now similarly in this case, so it's like a simple graph which will get constructed. Let's say there is one vector, now I'll insert one more vector, right? So this vector I'll see that इससे कितना distance है. This will come on again in the same space, and then I will connect these two together, right? Now there is a third vector which comes, and then this vector again I'll connect with A and B. Maybe so there would be one parameter which we will use to see that whether I have to connect or not. But let's say we're just building the vector, then this is how the graph will keep on evolving, right? And ultimately आपको इस तरह का graph हो जाएगा when more things are connected. But you can still see that maybe F is not connected with A, right? So there are two things that could have happened, right? Maybe F is less similar to A, and then F is more similar to C and B, to which we have shown a direct connection. And yeah, and then there could be a parameter, of course, we will use, because as I mentioned earlier, right, that all the vectors are similar to other vectors in the vector database. It's only the magnitude of similarity which is different, right? So then we say, let's take a parameter which we will say as M, the magnitude of similarity, and that M we will use to say that let's not connect more than beyond M, right? M तक ही connection रखते हैं. So we will say in this case maybe M is 2, or maybe 3 or 4 here. So maybe 4 M hai. So we say that okay, maybe it makes sense to connect this to a new incoming vector to A and not to the B, right? Because this is more similar to this. So how will you go about doing this, right? You will do a brute force. So when a new vector comes in, right? A new document comes in with an embedding. What you will do is in the existing space, we will do a cosine similarity with all of them which are already there, and then you will see no, this is more similar to this than these guys. And agar I'm still less than M, then let me connect to this and let me not connect to others, right? So these are some of the ways logic you will apply to basically construct this kind of graph as the index, right? Now how will search work? Let's say this is your query vector, green one is your query vector, and this is your existing product vector. So you will start with any random node, right? So let's say we are starting with A. And this could be a global node also, which you say that I will always start with this node. That is also okay. Or you will say, no, I can choose a random node to start search with. So let's say you started with A, and then you say that uh, you just only traverse the neighbors of A, right? So neighbors of A इसमें क्या क्या है? G.
One question, Kunal. So this
हाँ,
green that we see, right? So this query vector we have created using the LLM plus the embedding on RAG context, right? Who provides this query vector actually?
हाँ, क्वेरी वेक्टर हमने क्या किया होगा कि जैसे यूजर ने सर्च किया, राइट, मिंत्रा पे रनिंग शू,
Yeah.
तो उसको हमने लिया और हमने एक मॉडल के थ्रू पास किया होगा, बर्ट मॉडल विच यू वुड हैव होस्टेड समवेयर, राइट?
Okay. Okay.
You pass it to that and then you got that embedding for that,
Okay. Got it. Okay.
right? And so that is your this, but all these vectors, right, जो येलो में है यहाँ पे, उनको indexing time पे you would have done the same thing, right? तो जब वो when those product might have been created for the first time, you would have passed again to the same BERT hosted A model, right? And then you would have got the embedding and then you would have created this kind of graph, right?
Got it.
अब रन टाइम पे आपको एक क्वेरी आई, राइट?
Okay.
और सेकंड थिंग इज ऑल्सो यू डू इट दिस एवरी डे, काइंड ऑफ ये बैच में होता है, सो एवरी वंस इन अ डे, और यू विल से कि नहीं मेरा बहुत चेंज नहीं हो रहा, तो वंस इन अ वीक you will, for all the product vectors also, you will again pass it to the BERT and create an fresh embedding and then again keep on re-indexing, right? So this is a periodic activity which is done just for, let's say, नया कुछ product आ गया, जैसे मिंत्रा में या कोई भी thousands of products daily onboard भी होते होंगे, right? तो उनको भी आपको keep on indexing करते रहना है. And even for freshness, to refresh the embedding of an existing product, maybe there was some change done by the seller, right? So then also you want to recalculate those embeddings and then put it. So वो batch में भी करते हैं daily basis पे. So now this is so yeah, so now this, so you start with one node and then you say कि इसके neighbors क्या हैं, D, G and C, and then you compute the similarity, right? And then आप देखोगे कि जिससे similar है, you go ahead with that, right? And then let's say if you still keep on finding कि यार जो मेरे पास अभी जो मैंने similar pick किया है उससे ज्यादा similar मिल रहा है, तो you can proceed. But let's say अब उससे ज्यादा similar नहीं मिल रहा, तो you can give up, and then that gives you the result set, right? Let's say I started with this and then said कि D, E और F में कौन सा similar था, तो D ज़्यादा similar था in all the neighbors of A which I started, G and C. So I got to D because D was more similar. And then I said, I again for all the neighbors of D, I calculated, and then I see कि जो similarity यहाँ पे मिली है मुझे, that is that more than D or this is less than D? If it is more than D, then I'll just give up. I'll return D. But if I say no, these are still I'm getting more similar to my query vector, then I can still go and proceed. And then I, let's say, reached E, and then when I reached E, then maybe this is the most similar and I'm not getting, or I would have already traversed ये सब, right? E जैसे D यहाँ पे already traverse किया हुआ है, so then I will stop and then I will return. अब इस केस में आप ये तो possible ही है कि because the way we have constructed, it's possible that maybe F जो होगा वो ज़्यादा similar हो to the query vector. I'm just saying, right? Maybe F is more similar, but you are not able to reach F, right? And this is an approximation call that you have taken, because worst case में क्या होता है, right? Worst case or the best way to give the exactly, not exactly, but the most common, the most similar vector अगर आपको देना है, तो the best way is a brute force, right? Which is to go through all of these. But if you go with brute force, it becomes an order n operation, and then order n operation, you will not be able to do in the expected NFI, right? जो भी आपको latency 100 ms 200 ms में search करना है. Let's say these are 1 million documents, right? Or 10 million documents. Typical e-commerce will have like 10 million documents. Myntra has around 10 million documents. So आप ये कर ही नहीं पाओगे, right? So that's the reason you have to resort to some kind of approximation, right? उसके बाद फिर HNSW पे जाएंगे, that how this is solved into. This basically says कि one plane की जगह पे multiple planes हो जाएंगे, जैसे ये पूरा एक plane था. But I think this actually helped build that intuition, right? ठीक है, any question on this one, right, until this point?
Now you will cover, right, कैसे हो रहा है ये वाला पार्ट, right? मतलब
HNSW वाला, right sir?
हाँ मतलब प्रोडक्शन में जो ANN वाला होता होगा।
हाँ, मैं
Okay.
cover करूँ। ठीक है, तो पहले क्या करते हैं कि कुछ और देख लेते हैं एल्गोरिदम्स बिफोर वी फाइनली गो। आई थिंक इंट्यूशन एटलीस्ट समझ में आ गया होगा कि कैसे क्या हो रहा है अंदर। तो एक तो सिंपल एक के मींस क्लस्टरिंग एल्गोरिदम होता है विच इज वेरी नाइव, एंड व्हाट यू दे डू इन दिस केस इज यू जस्ट ट्राई टू क्रिएट अ क्लस्टर ऑफ ऑल योर वेक्टर डेटाबेसेस, राइट? तो आपने जो वेक्टर डेटाबेसेस बनाए होंगे, हाँ, तो आपने जो वेक्टर डेटाबेस बनाए, तो आपने स्टार्टिंग में तो यू जस्ट लेट्स से स्टार्टेड थ्रोइंग दोस वेक्टर डेटाबेस इन द वेक्टर स्पेस, राइट? बट देन you saw that automatically what you will see is that let's say all of those let's say e-commerce product which belong to a same category, they will be closer to each other, right? Then to the other one, right? So आप इसका एक क्लस्टर बनने लग जाएगा, दूसरे का थोड़े से कहीं और जाके वो सिमिलर क्लस्टर बनेगा, इसमें एक क्लस्टर बनेगा। सो नाउ आपको सिमिलैरिटी सर्च करना है, तो you what you can do is you can do an average of this, right? यहाँ पे इस क्लस्टर में सारे प्रोडक्ट्स को लेके आप एक एवरेज कर लो और उसको आप सेंट्रोइड बोल दो कि दैट इज माय सेंट्रोइड। सिमिलरली इस वाले क्लस्टर का एक एवरेज आउट कर लो और सेंट्रोइड बोल दो सिमिलरली यहाँ पे। एंड देन व्हेन यू हैव टू
सेंट्रोइड मतलब किसी एक वेक्टर को सेंट्रोइड बोल रहे हो उसमें से, है?
एवरेज ले लिया सर सारे वेक्टर्स का। तो यहाँ पे लेट्स से 1000 वेक्टर्स हैं, तो आई कैन जस्ट,
सेंट्रोइड इज अ न्यू वेक्टर देन, एवरेज ऑफ वेक्टर, ऐसा क्या?
हाँ मतलब नया वेक्टर नहीं आएगा, बट एक जैसे इसको मुझे एक मैट्रिक चाहिए, राइट? इन सबको इस क्लस्टर को आइडेंटिफाई करने के लिए, so I will use like that so that I can completely ignore these clusters and then I can just stick to this cluster, right? Because centroid अगर इसका 0.1 है और इसका नहीं, सॉरी, इसका 0.9 है और इसका 0.1 0.5 यहाँ पे है, तो I know that ये this is the cluster where I have to go for, and यहीं पे मेरे को सर्च करना है now, right? I can completely ignore this, right? These spaces.
Okay, ठीक है।
So and then in this, when I can ignore, because these are pretty distant in terms of cosine similarity, and then now I am on this space. Then in this space now I can look for other closer vectors, and maybe मुझे 10 return करना है, 20 products return करने हैं similar. So I can find in this, maybe I can do a brute force, for example, in this case, right? So I have to do a smaller brute force, and maybe I am able to reduce my search space by a factor of whatever factor, right? By that much factor, I'll be able to reduce the search space. So this could be a very naive way to do a vector search, right? हमने क्लस्टर्स बना लिया और एक ही क्लस्टर में हमें जाने की जरूरत है या दो ही क्लस्टर में जाने की जरूरत है, कुछ क्लस्टर्स तो हमने इग्नोर कर ही दिए होंगे, राइट? This is how I was trying to give a visualization on this. So
one thing actually. So this indexing, when we are doing this, so we can do it on this CPU, normal CPU and GPU also, right? It's like, so if you are using GPU, it may be faster because we have multiple dimensions. So where do we run this if we want to?
तो इसको मतलब सीपीयू पे ऑफ कोर्स वी कैन डू दिस इन सीपीयू। तो आपको जीपीयू क्या करने में हेल्प करता है, राइट? जितना मैंने समझा है, मतलब नॉट लुक कंप्लीटली इनटू जीपीयूज। तो व्हाट जो यू हैव टू डू अ डॉट प्रोडक्ट है, राइट? तो लेट्स से यहाँ पे एक तो इंडेक्सिंग के टाइम पे डॉट प्रोडक्ट कैलकुलेट किया होगा और सेंट्रोइड फाइंड किया होगा, राइट? सबका इन सब में सेंट्रोइड फाइंड किया होगा। तो आप कर क्या रहे हो कि यू वुड हैव टू डू अ लॉट ऑफ डॉट प्रोडक्ट्स, राइट? नाउ डॉट प्रोडक्ट इफ यू सी इट्स लाइक मतलब आप क्या करते हो उसमें, जैसे आप एक मैट्रिक्स लिया, उसका ट्रांसपोज मैट्रिक्स लिया, राइट? तो पहले को आप पहले रो के पहले बिट को पहले कॉलम के पहले बिट से मल्टीप्लाई करते हो, राइट? एंड देन सेकंड को सेकंड से करते हो, थर्ड को थर्ड से करते हो, एंड देन फाइनली आप जो भी आता है उसको आप ऐड कर देते हो, राइट? मैट्रिक्स मल्टीप्लिकेशन में। सो दिस थिंग इफ यू डू ऑन सीपीयू, तो आपका वो सीक्वेंशियली होता है ये काम। मतलब पहले को मल्टीप्लाई करेगा, फिर सेकंड को जाएगा, फिर थर्ड को करेगा। यही काम अगर जीपीयू में करोगे तो वो सबको एक साथ ही कर देगा। मतलब अगर उसमें जैसे 384 डायमेंशन हो,
we also have a million documents, so हम लोग उसको मतलब चंक में भी करके हर एक जीपीयू में जो भी होगा पैरेलली प्रोसेसिंग करके कर सकते हैं उसको. I mean, this is the place where I mean we are spend more energy actually, right? मतलब कि कहाँ पे हमारा जो एज अ प्रोडक्ट होगा, जो हमारा जो बनेगा एंड यूज के लिए, सर्चिंग मे बी द प्लेस वेयर the most energy will be going. I'm just asking actually, like because of this product we are doing, right? I mean, for the getting this
हाँ, तो
KME.
मैं वही बता रहा हूँ कि अल्टीमेटली ऑपरेशन क्या हो रहा है, राइट? मेजॉरिटी ऑफ द टाइम इट्स अ डॉट प्रोडक्ट व्हिच इज हैपनिंग, राइट? मैट्रिक्स मल्टीप्लिकेशन. सो मैट्रिक्स मल्टीप्लिकेशन इज हाईली पैरेललाइजेबल, राइट?
Yes.
And because it is highly parallelizable, if you do it over GPU, which can do it much faster, maybe 1,000 times faster than CPU, right?
Yeah.
तो वो आपको बेनिफिट वहां पे मिल जाता है. तो आप कर सकते हो सीपीयू में भी होगा ही, बट वो लीनियरली होगा. और जीपीयू यूज करोगे तो फास्टर होगा. उसमें हमने कुछ वेक्टराइजेशन वगैरह की चीजें देखी थी, राइट? हम जब बेसिक्स कवर कर रहे थे. तो इट्स ऑल्सो अबाउट हाउ यू राइट इट, राइट? जैसे अगर आप मैट्रिक्स मल्टीप्लिकेशन कर रहे हो और आपने फॉर लूप में उसको मल्टीप्लाई किया हुआ है, तो फिर वो उसका बेनिफिट नहीं मिलेगा आपको, राइट? फॉर लूप में जैसे हम करते हैं, राइट? रोप के ट्रेवर्स किया, फिर कॉलम पे ट्रेवर्स किया, फिर उसको निकाला और फिर बाहर जाके फिर ऐड किया, राइट? सबको. तो उस केस में वैसे हम करते हैं, तो वी विल नॉट गेट, इवन इफ यू रन ऑन जीपीयू वी विल नॉट गेट द बेनिफिट बिकॉज द कोड हैज नॉट बीन रिटन टू टेक एडवांटेज ऑफ हार्डवेयर एक्सेलरेशन. लेकिन अगर आप जैसे आपने जैसे उसको वेक्टर के रिप्रेजेंट किया हुआ है, मैट्रिक्स 1 इज 1 वेक्टर m एंड देन दिस n एंड देन m डॉट n किया हुआ है, अगर आपने या कोई लाइब्रेरी यूज की है जो इस तरह के सपोर्ट कर रहा है, तो और उसको आप जीपीयू पे रन कर रहे हो, तो दैट लाइन विल एग्जीक्यूट वेरी फास्ट, राइट?
Yeah, it's
So
being
that
4x,
is
140x more than CPU performance. K means if you are calculating K means on GPU, it's like a 4x to 140x from larger data sets. So that's the difference. Yeah.
सो मॉडल्स जो होस्ट करते हैं, राइट? जहाँ पे आपको एम्बेडिंग जनरेट करना है या फिर ये करना है, तो वहां पे यू विल सी दैट दे आर यूजिंग जीपीयूज बिकॉज आप वो क्वेरी टाइम पे कर रहे हो, राइट? देयर इज अ यूजर सिटिंग बिहाइंड, राइट? तो यू कैन नॉट टेक 1 second 2 second also, right?
Yeah, that's what.
You
Yeah.
have to do this in so typically मैं अगर कुछ NFR numbers throw करूँ, तो what we have seen is that this should be done, P99 should be around 25 ms for let's say 500 k RPM. 500 k RPM पे आपको लोड आ रहा है, तो 25 ms में you have to return. 25 ms में you have to return, so that, and then I think वो सब करने के लिए you will have to put, because there are a lot of parallel calls also, right, which is coming. 500k calls are coming in 1 minute. So this you will have to put it to GPU to CPU से, या तो बहुत CPU करेंगे तो वो फिर वो हॉरिजॉन्टल स्केलिंग इतनी ज्यादा हो जाएगी. दिस इज वेरी हॉरिजॉन्टली स्केलेबल प्रॉब्लम, राइट? आपने 500 के रिक्वेस्ट आ रहे हैं, आप बोलोगे कि ठीक है, मैं 10% रिक्वेस्ट को 1 बॉक्स पे 10% सेकंड थर्ड फोर्थ ऐसे मैं पॉड्स पे डिवाइड कर दूंगा. बट फिर आई थिंक वो CPU का कॉस्ट भी बहुत ज्यादा हो जाएगा, राइट? बिकॉज सो मेनी नंबर ऑफ कोड्स व्हिच यू हैव टू डिप्लॉय. तो मे बी देन वो GPU कर लो, GPU का एक या दो नोड ही उसको कर लेगा. आई एम जस्ट सेइंग, राइट? ठीक है. So this could be like K means clustering could be one very simple way to do this, right? उसके बाद ये देखते हैं फिर inverted file index. So inverted file index, I think ये यही करने की कोशिश करता है. Inverted file index, what it does, it whatever clusters are there, it will try to identify some partitions among them based on similarity, and then it will try to, whatever is your query, it will try to find एक सेंट्रॉइड से कंपेयर कर लेगा, एंड देन इट विल जस्ट रिजॉर्ट टू one or two groups itself, and it will ignore the other groups, and then it will return from one of those groups, right? Yeah. One thing is, I think there are two terms which are used, which is ANN and NN search. तो ये एक बार यहाँ पे देख लेते हैं. So of course in vectors you can only do a nearest neighbor search that we have already seen, right? You can only do similarity search. Similarity का मतलब होता है कि vector space में आप neighbor find कर रहे हो, right? What is the neighbor node or what is the neighbor product that you are trying to find? So the best for the user or user experience, the best thing is to return a nearest neighbor, right? But अगर आप nearest neighbor करने जाओगे, तो it becomes an order n problem, because then you have to compare with all of them, and and then you will be able to return, right? So you will not be able to do that in a vector space. It becomes very, very uh, compute intensive and time consuming. So usually जो यूज किया जाता है, राइट, विच इज ANN और approximate nearest neighbor search is यूज किया जाता है, which sees that okay, there would be a little bit approximation that I will say. मतलब when you return, let's say you have to return 50 products, 50 similar products, there could be few products out of that window जो नहीं आए top 50 में, लेकिन those might be more similar than those which you are returning, right? So it's not completely the top 50 most similar that you are returning here, but you are taking a trade-off. कि थोड़ा सा ठीक है, हल्का सा I am not exactly similar, but still I am able to serve this request within my expected latency of 100 ms, 200 ms, whatever, or 50 ms, whatever is the expected latency. So this is a trade-off which is taken, and that is the reason you will always see ANN and not NN search. So we use ANN to trade a tiny bit of accuracy for massive speed. Okay, this we have seen. I think these are all theory things, same thing I have explained.
So one thing, like, so this ANN and this nearest search, right?
Mhm.
So whoever has the matured model, that variation will be very less, right? I mean, they will be calculating the similarity, I mean, with very less errors, right?
Hmm.
Say that,
So
right? I mean, like, basically, when
Hmm.
the Bard came, I mean, like, not Bard, I mean, like, Google Bard came, right? I think that
Hmm.
case was like, it was giving very wrong results sometime also, right? So, I mean, maybe this calculation was not up to the mark, or maybe I'm not, I mean, that's why
नहीं,
maybe.
वो तो जो starting में this LLM problem which came with Google, right?
Yeah, yeah.
तो उसमें that was I think on LLM side when it was trying to generate some word, right? मतलब generative उसका वो था, तो it was generating very weird output, right? It was
Yeah.
not
So
something.
that's something maybe they do not have that matured this.
नहीं तो धीरज, उसमें LLM के अंदर I don't think कि LLM के अंदर vector database use हो रहा है, right? Vector databases it does not gets used
No,
inside
I'm
LLM.
just, whenever you're searching something, so it will be going to be some context, right? So they may have built some vector database for that context. So that context where they are putting those context, right? So, and they are applying the search. So that search and with that context is not that much matching. So I'm guessing actually what I'm not trying to say, right? So maybe for the Google initial cases, that may not be the right matured one. So that's why they have this problem. So I'm just trying to relate with whatever you're.
But underlying mechanism बहुत different है. LLM does not use vector database. This is more like when you want to, मतलब LLM में hallucination की problem होती है, right? And that you want to solve.
Okay.
Then you build in RAG app, and that will use vector database.
Got it.
Right? या फिर you don't use it for generation, right? जो मैंने search का use case बताया, e-commerce search का. There is no generation happening there, right? You're just using it for search. Right?
Okay. So this vector database will be specialized for our use cases. LLM is actually like general 20 billion parameter, 30 billion parameter, 1 trillion parameters. That is generalized, like frontier models, right? So frontier model don't use this kind of approach that what you're spelling using, right?
This is not. So in fact, vector databases जो है वो काफी पुराने हैं. मतलब ये 15 साल या 20 साल से already industry में है. मतलब don't quote me on the years, but what I'm saying is it's much more older than LLMs. LLMs तो 2022 में it became famous with ChatGPT, right?
Yeah.
This could be 2010, 2015, right? ये पहले से है. Only thing famous हो गया है because of these RAG use cases, and many companies now understand the value of it after this LLM wave, and then they start using it to compensate lexical use cases with vector, right? Lexical में, for example, simple सा अगर मैं बोलूँ, right? So you want to search that what should I wear tonight for party, right? E-commerce site पे. So there is no product where you would have written this word, right? Product description में लिखा होगा ये where should I wear this for party, right? So आपको वो किसी से मैच ही नहीं करेगा. लेकिन वेक्टर डेटाबेस में क्या होता है कि नॉलेज एनकोड होता है, राइट? सो उसमें कैजुअल ड्रेस या फिर इस तरह का इनफॉर्मल वियर, इस तरह की जो चीजें होंगी, उनकी भी एम्बेडिंग सिमिलर होगी व्हाट शुड आई वेयर पार्टी से, राइट? So that's the reason those will match. So
Yeah.
the typical use case वही है, sweet spot वही है कि where let's say your lexical will give you zero results, their also their vector can give you still some results, right? Because this
Yeah.
will match. So that is a sweet for such. This is nothing related to with LLM.
Got it. Got it. No, no, I was just, yeah. Okay. Makes sense. Thank you.
ठीक है, तो क्लस्टरिंग, एंड्रॉइड की परफॉर्मेंस ये छोड़ देते हैं सब. आई थिंक वी हैव कवर्ड दिस. This one is the edge problem. I think something we can see here, right? So what we did here is that we actually narrowed down to some clusters. We're saying, okay, now this cluster ka centroid jo hai, that is nearer to my query vector, so I'll just stay in this cluster itself and not search beyond that, right? So now there is a vector which is very near to this cluster, right? So those, and that might be very similar to the query vector compared to the centroid, right? And then you will miss out on those, right? So this is a problem here that you can imagine with inverted file index अगर use करते हैं for vector search. I think this we have seen. Now I think we can go to the HNSW. So HNSW is, so all these are like, so if I talk about this, or if I talk about flat index or clustering, all of these are like maybe some databases, initial databases would have used this, but these are none of these basically scale for production use cases. What scales for production use cases is the HNSW index, and this is again a typical. This is the standard index. So we will talk about some vector databases towards the end: Melvis, Vespa, Quadrant, Pinecone, and then you will see that all of them uses some form of HNSW index itself, right? So this is the production ready index which is used inside the databases, right? So let's talk about production, this one itself. Yeah, so अभी हमने ये जो देखा ना, so this was, we were talking, we are at one layer itself, right? We were in one plane. Now what we will do is we will go to multiple planes, and we will see that how multiple planes will try to solve some problem and then make this search even faster, right? Compared to one plane, right? So the core problem here is that even in this case, you're trying to find the nearest neighbor with still a lot number of nodes. So there's similarity search, which is basically a dot product that you have to do between query vector and the product vector. That is still huge. That is still large. And then because of that, again, uh, for matching and serving the user request, you will still take a lot of time. So the idea is that can we even reduce that further, right? Because ultimately हम search में क्या करते हैं, right? We want to reduce the order n problem to log n problem, and log n problem to order one problem, right? Which is a hashes या key value pair जो search करते हैं, right? So the best thing is if you can reduce it to order one or constant time, right? Where जहाँ पे कोई search ही नहीं हो रहा है typically, you just go for a key and then you find a value. So what is and how narrow you can do it, so that much lower will be your serving latency or search latency. So this is HNSW is typically which is helping here. This is the gold standard, right? So is what happens in this, right? Let's go through this. And I think Puneet sir, आप लोग भी किया होगा. I think we can brainstorm this, right? Okay, how this is basically helping. So HNSW algorithm uses a multi-layered graph structure to enable fast approximate nearest neighbor searches, right? It uses a multi-layered graph structure. So it combines the hierarchical express lane concept of skip list with a localized navigation of navigable small world. So ये दोनों skip list और इसको navigable small world, so NSW दोनों को use करके this is a new index which has been created, right? तो ये वाला I think I'll just try to zoom in here. I will discuss this diagram. So isme what you can see is now there are multiple layers. So one is layer 0 to layer 4. We have 4 layers, and the you will see that the bottommost layer hai, there you will have most of the nodes, right, which will be there on the the bottommost layer, and then the top layer will have less number of nodes. So as you go up from the lower level to the highest layer, you will see the number of nodes will reduce exponentially, right? So not linearly, but exponentially, you will have lesser and lesser number of nodes on the upper layers. Search will always begin from the topmost layer. When a new query vector comes, this is the query vector. Blue one is a query vector, and these are the yellow ones are the product vector. Search will always begin from the top vector. So अभी पहले तो इसका देख लेते हैं कि सर्च कैसे हो रहा है, then construction देखेंगे कि construction कैसे होगा इस index का. So let's say there is a blue vector. Now this blue vector, again, what you can do is you can always have an entry point which is assigned, right? And this you can say this is a marked point. So this query vector, again, you will compare with that entry point, and then you will try to find the similarity, cosine similarity between these. And then there is a parameter that you will use, which is called as EF search, and we will go into deep in that. So let's say EF search key value is 5, 10, or 50, or 100. So that says that how many neighbors of this particular node you will try to navigate on that same layer before you go to a layer below it. So let's say अभी यहाँ पे उसकी value जो है वो इसमें तो 1 या 2 ही possible है. So then you try to go to all those neighbors, and then you try to do a comparison and then do a similarity search between query vector and its neighbor, right? And then you say that then you compare the similarity score with the score that you got with this, right? And whoever is giving you the lowest score, right, you will stick to that node, and then you will go to the layer below to the node which is connected from that node, right? So then let's say अब इससे स्टार्ट किया था, बट इससे लोअर जो है इसके साथ है क्वेरी वेक्टर का सिमिलरिटी. तो देन वी वेंट डाउन फ्रॉम हेयर इंस्टेड ऑफ गोइंग हेयर, राइट? नाउ वी वेंट हेयर. Now on this layer again, we will repeat, basically it's the same thing which will happen on this layer also. Depending on the value of this, you will try to match that. Okay, किसका सिमिलर है, इसका सिमिलर है या इसके नेबर्स के साथ क्वेरी वेक्टर का कोसाइन सिमिलरिटी ज्यादा है, एंड देन जिसके साथ भी ज्यादा होगा you will again go back to the bottommost layer, and like that you will navigate to the final layer of HNSW. And final layer में you will find most of the nodes. What you do then is that you basically I think one thing, this I'm not sure, but one thing you can do is that you can keep collecting these vectors in let's say along with the scores, that kya cosine similarity, what is the cosine similarity score that you got with each of those nodes. So you can maintain that pair and the cosine similarity score, and then you can return, let's say आपको top 50 return करना है, top 100 return करना है from this algorithm, right? So this is how search would happen inside in this. So I'll just go through the text part of it. So insertion occurs sequentially, vector by vector. For a new vector, the following steps are performed. Layer 1 assignment, a maximum layer is randomly assigned to. So this is for insertion. I think like वो search का देख लेते हैं पहले, searching का. So searching follows a zoom in approach, moving from the coarse global shortcuts to a fine-grained local neighborhood, right? So यहाँ पे एक चीज what we need to understand is when we are starting from top layer, there would be, since this is exponentially lesser number of nodes on the top layer, very quickly we are able to go to the part of the graph where most of similar vectors will lie compared to query vector, right? So elimination जो है बहुत fast हो रहा है again. So if I go this, and then I am able to completely eliminate this side of the graph, right? So that is because there are exponentially less number of nodes on each of the top layers, right? Zoom-in approach, moving from coarse to fine. So the greedy descent, right? So search begins at the fixed entry point on the top layer, and in each layer above 0, the algorithm performs a greedy search to find a single single node closest to the query vector. So this is saying greedy. So greedy का मतलब ये है कि so I entered from this, and then the parameter which I have used, right? The value of the parameter, I'll only go till, let's say, 3 nodes or 5 nodes, and then whatever is the most similar I got, I just went down from that, right? So it's a greedy in that. It's not a brute force that you're not going to every node and then doing a comparison. That is not done inside this, because to save the latency. So it's like a greedy which will be done at the first layer, and then you will go down to find a single node closest to the query vector. And this node serves as a starting point for the search in the immediate layer below, right? Now, upon searching the bottom layer, layer 0, which contains all vectors, the search depth increases to EF search parameter. Now, let's say you are at the bottommost layer, right? Upon reaching the bottom layer, layer 0, which contains all vectors, the search depth increases to EF search parameters. So at this layer, okay, at this layer, it is saying that now, since I am at the bottom list layer, so there is a parameter which is tuned, which is available for tuning in config. So I will have EFS. So I will, so that much, whatever is the value of EFS, and let's say after navigation, I reach this layer. Now from that node, I will search for this much parameter, right? So EF search के amount का मैं searching उस level पे करूँगा. The depth search increases to EF search parameter. The algorithm maintains a dynamic candidate list. So this is what I was saying. It will maintain the pairs of what are the nodes which are similar to my query vector, and then it will maintain a similarity score. So similarity score, let's say 0.3 hai, 0.5 hai, 0.7 hai. So it will maintain that list, and always it can, let's say it only needs to maintain return 50. So it will always keep on dropping. If more similar vectors are there, it can keep on dropping the ones which are of a higher similarity, right? The cos theta value is higher, right? So those it can keep on dropping from that candidate list. So the algorithm maintains a candidate list of the closest points found so far. It explores neighbors of these candidates and continues until the list of the closest results cannot be improved. All right. Result: the top closest neighbors from the final list are returned as the search result. So this is about search. We'll look at the insertion also before we go to the construction parameters. Now what happens in case of when you have to insert, right? So insert के time पे क्या होता है कि randomly there is an algorithm which will be used to figure out which layer I have to start the insertion from. So it could be layer 1 or layer 2 or layer 3 or maybe layer 4. So or layer 0. So let's say we start with some layer, right? Let's say we start with this layer. Now for that layer, I think let's go through the text, right? So insertion occurs sequentially, vector by vector. For each new vector, the following steps are performed. So layer 1. So a maximum layer is randomly assigned to using a exponentially decaying probability. So which layer will be used, right? 0, 1, 2, 3. So this is a formula. This is the algorithm which is used, exponentially decaying probability. So जितना ऊपर जाओगे उतने कम chances है उस layer का select होने के लिए initiation start करने. Maybe it will not start from the topmost layer. Maybe it start from, there is a more chance to start from the lower layers than compared to the top layer. Most vectors stay in the bottom layer while exponentially fewer reach the top layers. Upper layer traversal. So starting from a global entry point at the highest layer of the index, the algorithm performs greedy search to find the single closest node to the current layer. So let's say whatever layer we chose, right? At that layer, this is covered here. Okay. So let's say we got layer 2 where insertion should have happened, right? So it will find it will go to top from that layer, and then from top layer it will find which is the node which is most similar to this particular node from where I have to start the insertion. So starting from the global entry point at the highest layer of the index, the algorithm performs a greedy search to find the single closest node in the current layer. Once the closest node is found, it becomes the entry point for the next layer down. This continues until reaches the assigned layer. Okay, what layer that we chose at step 1, once it reaches that layer, till that point, it will continue finding using greedy, right? So in each layer down to 0, a more thorough search is performed using EF construction. From in each layer down to 0, a more thorough search is performed using EF construction parameter to find a set of candidate neighbors. Yeah, so search same thing it is doing. It is trying to find the candidate neighbors using this parameter. This parameter we will look into it, but it's trying to find who are the candidate neighbors जिससे मुझे connect करना है similarity, right? So from these candidates, neighbors are selected from bidirectional links with heuristic selections. So this is important. Heuristic selection is important, and why this is important? Let's see this. So for example, अगर query vector is similar to this, so query vector is likely to be similar to this also because these two are very similar and they are connected. So इसका मतलब है कि अगर आप यहाँ से edge draw कर रहे हो, then this edge also you should draw. But if you do like this, then this node you will draw to all the nodes you are drawing and to all the neighbors of that node also you will draw, right? So this you'll have to stop this somewhere, right? This will go in loop. So what is done is, first I think एक तो parameter m use होगा, which will say कि I'll connect only to these many nodes and not beyond that, right? And the second thing is you will use a heuristics. So this is not exactly deterministic. Heuristics use करेंगे यहाँ पे. To ensure that the graph remains navigable, the algorithm often uses a diversity heuristics rather than just picking the closest. So instead of just picking, say, this is the most closest and I should draw an edge here, it will just use a heuristics to connect to one of the similar nodes instead of doing the exact similar node, right? So it avoids connecting to the neighbor if that neighbor is already very close to one's existing connections, right? So this talked about. And pruning is if an existing node exceeds the maximum allowed connections. So there is a tuning parameter, and of course the connection sometimes will be more than that parameter. So then we will be pruned, and pruning will be done in exactly the same way, where we will say that जो most dissimilar है उसको prune कर देंगे, उसको remove कर देंगे, right? So this is on inserting and searching in this graph, but we will look into this again using these parameters, right? So M is the maximum connections, right? So this is one node. What is how many times one node will be connected at most to the 3 nodes or 5 nodes or 10 nodes? So this defines the maximum number of bidirectional links established for each node in the graph layer. Higher M improves the recall and search speed via better shortcuts, but significantly increases memory consumption and index build time, right? So this you can understand. जितना higher M की value रहेगी, उतना similar जो है, you can find. I think you will get more closer as exact results, right? But it will also come at the cost of memory and build time, because build time pe again, yeah, Dheeraj.
No. I'm just going to. I'll ask you later.
So build time pe again you will have to put that many indexes, तो उतना ही ज़्यादा time लेगा ये. और again search time pe also you'll have to traverse that many nodes, right? So search time will also increase. So typically इसकी value जो है, that is kept between 8 and 14. I think default I've seen somewhere is 16, but we can tune this between these values. 16.
So this M is the actually for each layer actually, right? It will change for other layers.
Each node पे layer का I think should be at each layer, but you can see this.
Yeah, I was just seeing the table you're saying. M is different in each layer. Layer 0 has a M equal to 4. Layer 1 has M equal to 3. Layer 2 is M equal to 2.
Okay. हर layer के लिए we can tune it.
Yeah.
Okay. Then EF construction. EF has 2 parameters: EF construction and an EF search. So EF construction is of course जब आप इंडेक्स बिल्ड कर रहे होगे, सो बिल्ड टाइम सर्च डेप्थ तो कंट्रोल्स हाउ मेनी कैंडिडेट नेबर्स आर एक्सप्लोर्ड ड्यूरिंग सर्च इंडेक्स क्रिएशन, राइट? तो सिमिलर आपको अब एक नया नोड आया, उसको आपको कहीं पे पुट करना है, राइट? सो हाउ विल यू डू इट? सो यू विल यूज दिस पैरामीटर ईएफ कंस्ट्रक्शन. तो कितने नोड्स के साथ आप सिमिलरिटी सर्च करोगे बिफोर यू पुट दिस, हाउ मेनी कैंडिडेट्स नेबर्स आर एक्सप्लोर्ड. So EF construction leads to a higher quality graph. Yeah, it's a higher quality graph and better recall, but increases indexing time. Indexing time it will increase because now you have you will be more neighbors are connected. How many candidate neighbors are explored? You will be exploring lot many candidate nodes before you insert it. So it does not affect the final index size. Index size पे फर्क नहीं पड़ेगा because कहीं ना कहीं तो आप उसे index करोगे, right? आप उस लेयर पे करोगे या नीचे करोगे, बट इंडेक्स, दैट्स द रीजन इंडेक्स साइज विल नॉट differ because of this parameter. So commonly set between 100 and 500 and the thumb of rule is set to at least twice the value of, I think m होगा शायद यहाँ पे, मिस हो गया, twice the value of m होगा, but this we can look. So this is commonly set between 100 and 500, that how many candidate nodes that you will be exploring when you insert that. EF search is the query time search depth. So determines the size of the dynamic candidate list maintained during a search. Determine the size of the dynamic candidate list that is maintained during search. So this is like जब हम search कर रहे होंगे, right? So how many dynamic candidate list is maintained during search? Okay. So I think जो candidate list की हम बात कर रहे थे, right? कि इतने candidate list होंगे जिसके साथ उसे finally उसको 50 return करना है, but what is the size that will be maintaining a little higher than that size? Determines the size of the candidate list during search. So increases search accuracy at the cost of higher query latency. Increases search accuracy at the cost of higher query latency. Yeah. So search. So the more number of dynamic lists that you can maintain, right, you will have a more accurate search. मुझे थोड़ा समझ में नहीं आ रहा because the candidate list will narrow down eventually to that set itself, right? How much you have to return only, that is what you should be interested in. Cost of higher search latency. Then unlike this is the query time parameter that can be tuned per search without rebuilding the index. Okay, then this is maybe that value itself which we are giving in that, let's say I want 50 results or I want 200 results. So this I can pass on every time when I'm querying, right? So this is like a limit in MySQL, right? You finally return this much value, limit 0 to n. Consider it might be greater than or equal to the number of requested neighbors.
So
this might be greater than or equal to number of requested neighbors. So this is the candidate list size. Yeah.
So in every layer, it will be finding some neighbors, and then it will be putting it in the candidate list, right? So depth, this query time search depth is like someone is providing that, right? I think we can define it, or we can define it.
जो मुझे समझ में आया, राइट, धीरज, इससे इसमें ये होगा कि जैसे आप ग्राफ ट्रेवर्स कर रहे हो, राइट? अब आपको फाइनली कितने रिजल्ट सेट रिटर्न करने हैं, राइट? सो दैट यू विल मेंटेन अ लिस्ट, राइट? And you will keep on pruning the list as and when you find a more nearest neighbor.
Right? Actually, you will be starting from the top layer, right? Layer 4. So you will be keeping the, I mean, because you are doing the nearest search, right? Kind of thing. So you will be putting all those, whatever you found in that particular layer, you will put it in that candidate list for that particular layer. Then you go further down below. And at the end, you will...
list तो एक ही होगा ना? हाँ? Candidate list तो एक ही होगा. That's like what is your result set going to be, right? Ultimately, your candidate set will be part of
it will be only one, but what I'm saying that candidate list will contain the elements from the each layer actually. So you move from layer 4, layer 3, layer 2, and at the end it will choose the one that is the most desirable for your use cases. I mean, you want 50 use cases, then you just combine, just pick the nearest 51, right, from that list.
Yes.
So we define that in that search criteria also. I mean, user defines it, or is it already defined? I mean, that depth, at which depth we need to go, that you were saying, right? Depth.
So usually वो use case पे define होगा. So for example, let's say you are searching for some page, right? So on that page, maybe you think कि pagination can go to, let's say, 10 page depth, right? Then you say कि अगर हर page पे मुझे 5 या 6 या 10 दिखाने हैं, so then it will be 100, right? So you define based on how many candidates that you want, right? अब कोई और पेज है जिसमें कम रिजल्ट दिखाने हैं, देन यू विल से कि आई वांट इन ओनली दिस मच रिजल्ट्स, राइट? मतलब समझ गया ना, ये तो
Yeah,
दिस इज योर यूज केस, राइट? ठीक है, एक बार लेट्स जस्ट गो थ्रू दिस if there is insight from this diagram. So this is basically saying iterable index enables fast vector search even at large size and builds an algorithm multi-layer graph that balances speed and search quality. So we're just talking about how this graph is built: higher layer exponentially fewer nodes compared to lower layers. And upper layers enable faster traversal and lower layer enables detailed searching, right? So quickly we are able to go deep, and then यहाँ पे जाने के बाद bidirectional connections enabling neighborhood based searches. Yes, and lower layer enable this. ठीक है. HNSW search, vector search in
हाँ,
HNSW.
मुझे एक चीज मैं समझ में नहीं आ रहा, इसमें इंसर्शन में एक इसमें स्टेप में आ रहा था लेयर असाइनमेंट है, पहला जो
हाँ सर.
स्टेप है। तो लेयर असाइनमेंट
हाँ,
मतलब क्या है कि अ,
अब किस लेयर से स्टार्ट करोगे?
किस लेयर से स्टार्ट करोगे? अच्छा, मतलब इंसर्शन फाइनली बॉटम लेयर में ही होना ही होना है बॉटम लेयर बी, राइट?
तो मैंने जो देखा है उसमें ऐसा लिखा था कि मोस्ट नोड्स विल बी देयर इन बॉटम नोड्स, बट ऐसा नहीं लिखा था कि 100% ऑफ नोड्स विल बी इन बॉटम नोड.
नहीं, आई थिंक नहीं है। जो सर्च में तुम्हारा सेकंड स्टेप है रिफाइंड सर्च, वहां पे लिखा है ना विच हैज ऑल द वेक्टर्स, तो वो लग भी रहा है मुझे ऐसा ही कि उसमें ऑल द वेक्टर्स होने ही चाहिए फिर लेयर जीरो में, मतलब।
yes, yes.
इसका कह रहे हो क्या, इन
हाँ
ये
हाँ,
वाला? तो इन ईच लेयर
बिलो वन रिफाइंड सेकंड जो बुलेट पॉइंट है रिफाइंड सर्च, तो बॉटम लेयर में उसको मतलब इट हैज ऑल द वेक्टर्स, तो मतलब फाइनली इसमें तो मतलब बॉटम लेयर में इंसर्ट होना ही होना है क्या, ऐसे मतलब लग रहा है, राइट?
हाँ हाँ, इसके हिसाब से ये है. कहीं पे मैंने मोस्ट भी पढ़ा था, तो थोड़ा सा ये अलग इम्प्लीमेंटेशन हो सकता है या ट्यूनिंग के बेसिस पे हो सकता है. बट आई थिंक सो मैं यहाँ पे आई थिंक ये कहने की कोशिश कर रहा था कि तो एक तो होता है कि पहले जब इंसर्ट करे तो एक लेयर वो रैंडमली सेलेक्ट करता है, राइट, ह्यूरिस्टिक्स के बेसिस पे. ये लेयर 2 से मैं स्टार्ट करूंगा या यहाँ से स्टार्ट करूंगा, स्टार्ट करूंगा, राइट?
वो
बट
सर्चिंग।
वो हाँ, फाइनली वो बॉटमलेस लेयर पे जाके इंसर्ट होगा, इसके हिसाब से ये लग रहा है सर.
हाँ हाँ, लेयर इंसर्ट तो बॉटम लेयर पे ही जाके होगा।
हम्म.
मे बी वो है ना तुम्हारा जूम इन वाला जो कॉन्सेप्ट है इसमें कि वो किसी रैंडम लेयर पे जाएगा और फिर उसके नीचे मतलब उसकी एंट्री फिर ईच लेयर फ्रॉम दैट लेयर होगी एंट्री फिर, ऐसा क्या? जैसे मतलब लेयर 3 पे असाइन हुआ तो लेयर 3 और लेयर 4 पे उसकी एंट्री बने,
लेयर 3 और लेयर 4 पे एंट्री बने.
अदरवाइज लेयर असाइनमेंट का मतलब ही क्या रहा फिर, अगर उसमें लेयर में एंट्री हमने नहीं करी करी तो उसका मतलब क्या रहा, राइट?
करेक्ट. हाँ, इस लेयर का मतलब क्या रहा, करेक्ट.
तो ऐसा लग रहा है लेयर 3 पे भी एंट्री मिलेगी और लेयर 4 पे तो इवेंचुअली मतलब बिलो लेयर्स पे तो सबको एंट्री होनी है फिर, अगर ऐसे देखा जाए ना इसको।
हाँ, बिलो लेयर पे नहीं रहेगी तो आपको हो सकता है कि आप कैंडिडेट भी ना रीच कर पाओ, राइट?
हम्म
फॉर एग्जांपल आपको जितने रिटर्न करने हैं वो आप रीच ना कर पाओ, बिकॉज आप
हम्म
आपने यहाँ पे पार्टीशन कर, इट्स लाइक अ पार्टीशन एंड देन यू नेवर रीच दैट नोड, राइट? सो इट मेक सेंस कि लेयर लास्ट लेयर पे सारे के सारे नोड्स रहे.
या
ठीक है, एक बार मैं भी थोड़ा सा और क्लियर हो जाएगा ये. Okay, so HNSW proceeds by starting at the top layer and proceeds down. How would HNSW search for this vector work, right? So start at the top layer, find the most similar nodes, and travel down, repeat until, then find the closest key nodes. Okay, it's the same G there. HNSW parameter can be tuned for speed and quality. So EF is the size of the candidate list used to keep track of the top results. EF construction is the size is the candidate list used during new vector insertions. Distance metric used to compare, so this is cosine or dot, and maximum connections is the M जो हमने देखा था, that is the maximum number of connections possible at each node. हाँ, insertions का आप कह रहे हैं ना, building a new HNSW index works similarly to each search. The best location for a vector is determined through a search. Where would the vector be inserted in the HNSW graph? Starting from the top layer, find the most similar node, travel down, repeat until the bottom layer, and find the closest k nodes, and insert new node and create a new connection. तो इस केस में ये कह रहा है कि हम टॉप नोड से स्टार्ट कर सकते हैं इंस्टेड ऑफ लेयर असाइनमेंट, एंड देन वी कैन गो टू द बॉटम मोस्ट नोड. सो आप टॉप नोड से स्टार्ट किया तो आपने देखा कि ये 3 नोड है which is most similar to this, and then you go down from that, and then you repeat the process, and last node pe then you connect to that m number of what is your m nodes to all those m connections that you can make on the last node. Okay, so I think this we have seen. So I think HNSW पे इतना ही है. एक बार सर आई कैन आस्क दैट क्वेश्चन राइट, आप एक बार क्विकली पूछ लेते हैं. आप बताइए एक बार क्या बोल रहे थे, just to clarify,
हाँ,
right?
मतलब
does the
is like or all vectors mandatorily present on the bottom layer, वो क्लैरिफाई कर सकते हैं या उसका एक्सेप्शन है?
मैं वॉइस यूज कर लेता हूँ. Will the insertion happen at all layers or
0th layer actually.
हाँ
all layer पे तो नहीं हो ना,
Already new one.
at the
bottom layer.
big layer or
0th.
always happens
नहीं, ये क्लियर नहीं हो रहा क्वेश्चन. डज इंजर्शन फॉर ईच वेक्टर ऑलवेज हैपन एट बॉटम लेयर, पूछ लो तो वो शायद समझ में आएगा. इंजर्शन फॉर ईच वेक्टर ऑलवेज हैपन एट बॉटम लेयर.
In HNSW, right?
नहीं, वो तो कॉन्टेक्स्ट मैं वही डिस्कस कर रहा था यहाँ पे, समझ आया.
अच्छा.
In the context of HNSW algorithm used by many layers, yes, vector is always inserted to the bottom layer, but it may also be inserted into several layers above it.
Correct. That's clear.
That is clear. Okay.
Understand?
Oh, 100%, 10%, 1%, and 0.1%. Okay, and like that they have a layering. Okay.
ये जो probability वो था ना, degrading probability at each layers.
Decaying probability, yes. Okay.
Decaying, yeah.
ठीक है.
Okay. So अभी this is in short among the different databases. I think मैं Vespa का cover कर सकता हूँ because Vespa I looked into little detail. The screen is coming up. So so now one of the databases, vector databases, is Vespa. So Vespa is actually a hybrid database. So it supports both vector also, and then it supports lexical search also. So Vespa में how it is there at so ultimately एक बार ये देख लेते हैं कि so there is lot happens inside a database, right? So there is an index, then there would be a query engine, there would be a storage layer, there would be different read and write paths inside a database, right? How read happens, how write happens. So core vector databases का में आप देखोगे तो core रहेगा वही कि there is an HNSW index. So there is a insert path, and then through the insert path you send your documents, and which is called as feed path in case of Vespa, and that document is so basically आप outside embedding या तो आप बाहर कर लो. Again, different databases will have different flavor, that you give a text input, and then in databases like Vespa you can also because they have separated it, so you can it can take a text itself as an input, and then here you can plug a model, and then यहाँ पे वो model से embedding generate कर लेगा, and then it will store it. But otherwise, in most of the databases, what you will see is that you will have to give an embedding. So you have to host embedding as a service, and then you call with your query, user query, you get the embedding, and that embedding then you use it for search. Okay, so that is so this is one thing. Second is of course the indexing. So indexing time pe, of course, you will have to take all the documents and then again pass into the vector database, and then it has to generate that index itself, right? So search जो हो रहा है वो तो similarity search ही हो रहा है, right? तो कोड तो यही है जो हम लोगों ने पूरा देख लिया, बट इन एडिशन टू दैट some vector databases will what it can do, right? It can do a pre-filtering, it can do a post-filtering, or it can do simultaneous filtering, right? These are the three types which can come. Matlab, let's say it's looking at the HNSW index, and while it is looking at the अब आप ऐसा बोल सकते हो कि मुझे वेक्टर डेटाबेस सर्च करना है, बट मेरे पास कैटेगरी है एक, जो which I have already figured out maybe from my query understanding layer or some place, right? Now I don't want I want to divide it. जो मेरा result आएगा, that result should be from this category itself. It should not be from other category. It does not. I don't care about the other category, right? So you can implement a pre-filter, right? So pre-filter में आप what you will say is that where category is equal to shoe, only those only that much search space I want to search, right? So maybe I'm just saying, right? Maybe one way could be कि मैंने अपने जो HNSW है उनको ही मैंने divide कर लिया category level पे, right? And if I divide it by category level, my search space reduced drastically. It's like a sharding which I have done, right? Sharding based on a category. So now, since my search space reduced a lot, I can search would be much faster. So that is one way to do it. But the other way to be do it could be कि there are some filters that we apply, right? Let's say हम Flipkart पे गए और Flipkart पे you can say कि the price should be between 200 to 500, or it should be serviceable at this location, or color जो होना चाहिए वो shoe color should be black and white only. So when you these are the post filters that you can apply. And when you apply these post filters, then you want a result from this, but you also want attributes to be returned. And then from those attributes, you will say, okay, these are only my final candidates, right? So it's like a post filtering that you do, a pre filtering you do, or one could be ki when you are navigating the HNSW index, at that point itself, there are whatever filters that you have, right? You keep pruning from the filter also. That is, similarity to बहुत अच्छा है, लेकिन this does not match my filter, so I'll drop this, right? So that kind of, so there could be three ways to basically do all of this and build on top of this index, HNSW index, right? Which typical database can support. But I think so. Generally, the understanding looks like कि pre-filter जो होगा that may work better. So अगर pre-filter से हम complete sharding कर पाते हैं, so then I think of course pre-filter should work better, right? In my understanding, because now your search space completely narrowed down by 1/10th, 1/15th, or whatever number of categories you have. But उस केस में क्या होगा कि आपको कुछ तो ऐसी queries होंगी ही जो क्रॉस कैटेगरी होंगी, and in that case it becomes scatter gather, or you will have to go to all of those all of those HNSW, and then the slowest one will determine what, because after you will have to take result from all of them and then merge it. The slowest one will determine what is the speed of your search, right? Or and in case of post filtering, there one risk that I see in post filtering is कि आपने कैंडिडेट सेट निकाल के लिया है और फाइनली आपका पोस्ट फिल्टर से कोई भी मैच नहीं किया, so then you don't have anything to return to the user, or you have lesser number of final result to return to the user than what you intended to return, right? तो आपका कैंडिडेट लिस्ट ड्रॉप हो जाता है. So that's a risk with post filtering, and that is usually solved by getting a much higher candidate set, right? So आपको फाइनल रिजल्ट तो 50 ही करना था यूजर को, लेकिन आप 200 लेके आओगे एक्सपेक्टिंग कि 5 maybe 100 or 150 भी ड्रॉप हो गया, तो I'll still do a good job of returning to my user. So this is how it is usually solved, post filtering के problem, right? But NFR wise, I think there is no one answer here. It will depend on that context, that which gives you a better NFR, pre-filtering and post-filtering. But some of these could be, let's say आप कुछ चीजें आप embedding में bake in ही नहीं कर सकते, right? For example, maybe discount पे filtering है. अब discount, maybe you don't want to bake into the embedding of the product, right? You want to keep it always outside. One reason could be that it could be a very fast moving, right? And then so whatever fast moving is there, again, if you go and update that into the embedding, आपका इंडेक्सिंग का टाइम भी बहुत ज्यादा, मतलब इंडेक्सिंग आपको उस रेट पे मिल ही नहीं पाएगा, बिकॉज एवरीथिंग इज गोइंग इंडेक्सिंग एंड देन अपडेटिंग दिस ग्राफ, राइट? इज वेरी डिफिकल्ट टू अपडेट दिस ग्राफ, very time consuming to update this graph, right? So So these are the some of the calls that has to be taken. Right, sir? ये सब discuss करते हैं, right? When we want to set up these
या
this,
दैट इज ट्रू,
right?
दैट इज ट्रू। वो है, मतलब ये तो है, इनिशियल शार्डिंग वो आपको करनी पड़ेगी, जिस तरह की आपकी क्वेरी में भी कैटेगरी बेस्ड शार्डिंग और वर्टिकल और स्टोर बेस्ड शार्डिंग, वो तो है इम्पोर्टेंट। यस। और दूसरा
But what
ये भी एक क्वेरी बहुत कॉमन भी आती है, मतलब हमारे यहाँ आप देखोगे ना, मतलब इस इंफ्रा पे लोड उतना नहीं रहता। आई थिंक 95% कुछ हिट रेशियो रहता है हमारा केसेस का। और
95% कैश हिट रेशियो है?
हाँ,
काफी अच्छा।
90% 95% कैश हिट रेशियो रहता है, बहुत ज्यादा कैश तो जाता है इसमें।
हम्म।
यस।
तो आप कह रहे हो कि मोस्ट ऑफ द टाइम वो क्वेरी वेक्टर जो है वो सेम ही जनरेट हो रहा है, या क्वेरी सेम जनरेट हो रही होगी रादर?
हाँ, क्वेरी मतलब यूजर क्वेरी ही सेम आ रही है ज्यादातर।
हाँ,
तो
तो आप
काफी
कैश
लेयर्स। हाँ, मतलब
यूज
हर
करते
लेयर पे कैश है, वॉट एवर हमने L0 लेयर 1 लेयर 2 कैश, मतलब हमारे यहाँ कई तरह की आपने देखा ना, सर्च जो कई तरह की है, राइट।
हो।
कई लेयर्स पे
हम्म
तो कैश हिट ही होता रहता है। दैट्स ट्रू। बहुत हद तक। रिपीटेड क्वेरीज बहुत होती हैं।
तो उसमें आई थिंक P99 हायर होगा, बट जो बाकी जितने
करेक्ट।
भी कैश हो गए, राइट, वो तो आपको बहुत ही विल गेट अ
फास्ट।
गुड, वेरी गुड लेटेंसी, वेरी लेस लेटेंसी ऑन दिस।
या
बट वो कैश फिर आप लोग यू विल बी ओनली कीपिंग फॉर 5 मिनट्स और 10 मिनट्स, राइट? तो उसके क्योंकि वो स्टील भी हो जाएगा बहुत फास्ट।
हाँ, डिटेल रहेगा तब भी, मतलब वो ये, मतलब तब भी उसके बाद भी बता रहा हूँ, ये रिजल्ट जो है डिटेल तो रहता ही है।
ठीक है, तो एक बार क्विकली लेट्स गो थ्रू दिस। सो Milvus is one of the vector databases. This is kind of a cloud native architecture. So Milvus is built on microservice architecture, separates compute from storage. So unique approaches, log as data approach. It uses a message queue like. So I think what it's saying is that for indexing data into vector database, it's using these kind of queues. एंड ये क्यू या टॉपिक यूज करके इट्स एबल टू से दैट ओके, आपने मुझे दिया रिक्वेस्ट को, एंड आई विल गो एंड अपडेट HNSW इंडेक्स at a rate at which I can go and update, but I have accepted your request and I have put it into a queue. So इसमें reflection time आपका जो होगा finally when you search, right? So that time you will see that whatever I insert immediately, that's not immediately searchable, and there would whatever queue का जितना build up time है, processing time है, उतना time it might take to return finally in the result, but it's at least able to quickly take up that data during insertion, right? It can a massive amount of stream data without slowing down the query nodes. And यहाँ पे ये separation is the most important thing. So compute और storage को separate कर दिया इन्होंने. So compute is basically you will use it at the time of read, right? So read is now happening on that index, and then write जो होगा उसको इन्होंने queue में डाला है, and slowly from queue they will pick and then update the index. So that's the reason they were able to separate these two, compute and storage. So massive storage scaling, and you have a billions of vector, you just add more query nodes. And then write nodes, I think read nodes, you can do a replica. So you add as many read nodes as you want to do. So read scaling is pretty easy by doing more number of replicas. But that also causes problem with write, because now write will have to do write at all those nodes. So I think that they will solve using this thing, right? Quadrant, focusing on memory safety and extremely low level optimization. So I think this is the sweet spot here. So quadrant में आप जैसे ये इस तरह की filtering you can do simultaneously when you are doing HNSW search, right? So it allows for payload filtering. So directly during the search, instead of searching vectors, then filtering by this, like a post filter, right? So आपने search कर लिया, उसके बाद आपने देखा price किसके इतने कम है, and then only I have returned. So it does both at the same time within the graph itself, right? So very high throughput and efficiency, and it offers the choice for developers who want a single binary or a high performance local edge deployment. Yeah. The Pinecone, what it does, it uses, it's like a leak kind of a concept. So it uses blob storage where it will put the vectors. So you don't manage shards or cluster. They recently moved to a serverless architecture where they will put data into, let's say, a blob or a lake, and then compute is spun only when the query hits. So this is very clear separation of storage and compute. But इसमें of course latency वगैरह आपको नहीं मिलेगी, right? सही लेक में आप blob में store करोगे तो आपको latency नहीं मिलेगी, right? So this will become like a typical data warehouse versus data lake problem, right? But this is giving you a separation on compute and storage, which is a strength of a data lake. So system zero operational overhead, and it's a vector as a service. Yeah. This Vespa is basically so Vespa में क्या होता है कि Vespa supports three kinds of indexes. So it will support one is your attribute index. So attribute index is like जैसे हमने MySQL के हमारे indexes हैं, right? So we can do an index on any kind of price, discount, इस तरह की values पे. Then it also supports inverted index. Inverted index with something like Solar or yes, Elasticsearch supports. So it takes your document and then it scans all the keywords in that document, and then it creates a reverse index. You will those keywords. What are the documents which are present in those keywords? It will maintain a pointer to those documents. So that is inverted index. So that is also supported, and then HNSWBA. So this for these two indexes, right? Attribute indexes and HNSW. It can go and update. So HNSW is again RAM based. It's completely in memory only. And attribute index is also you can maintain. I think attribute index we can maintain on disk also, on memory also. This one is usually maintained on disk. So we have seen that in इसमें inverted index जो होता है इसमें there is a problem with segmentation, right? So you basically this you can do a point update, right? So you can find the location where that attribute is stored and you can just go and update that index. HNSW में also you can do a point update, right? But in case of documents, you don't do a point update. What you do is you create one more copy of the update, and then at the time of reading, you'll have to look at both the copies. So it slows down your read, but write both fast because the segment आपने something like a mem table you created and then you flush that mem table and it becomes a segment, like similar to big table में या Cassandra में, right? And now you have multiple segments, so you need to run a compaction here, right? So after compaction, both these segments will be merged and then it will become one segment. But till that time, we'll have to look through all the segments and then do the reading or serving. So Vespa supports all these three kinds of indexes, right? So yeah, this is Yahoo, and the top Vespa allows you to run actual machine learning models. One of the unique things about Vespa is this separation of query node from content node. So content node is where your actual data will reside, and then container node is basically यहाँ पे आप query parsing, query rewrite, ranking और result जो भी होंगे, right? So there could be n number of content node. जितने भी content node हैं, so वो सारे से आप data को लोगे and then you will do a merging here at the container node. So जो indexes वगैरह हैं, those all the indexes and your actual data reside at this layer, at the content node layer. But at the container load layer, you do all these things, right? Which is written here. So in this case, what you can do is at the container node, now you can also plug in models. The model which I was talking about, right? So you can say कि यहाँ पे मैंने एक ONXX, which is ONNX. So open neural network based कोई भी model I can put, and then I can give it a text query itself, and it can pull the embedding and then pass it to the HNSW. Or and then I can use a re-ranking model also, right? यहाँ पे. So I can say that my result which I got from this layer, from this layer, that is sorted based on cosine similarity or some similarity or BM25, right? In case of lexical. So that is sorted by that, but then I will use a re-ranking model, right? यहाँ पे आप एक और कोई भी मॉडल यूज कर सकते हो विच विल से दैट क्वेरी, इस क्वेरी के साथ जो ये डॉक्यूमेंट आया दैट इज मोर सिमिलर, so you can reorder that. So that ranking model also you can plug at the container node level, and then it can return the result. So usually all these things are done at a different layer, and this problem is solved at different layers. So outside database हम solve करते हैं, हम outside database एक re-ranker layer लगा के रखते हैं, outside database हम एक embedding pull करने के लिए हम service लगा के रखते हैं, but Vespa additionally gives this capability inside this database itself. And also Vespa can do all these three kinds of lexical search also, uh, compared to that one, right? It can do lexical search plus vector search plus attribute based search. All of these it can do. So unlike others, TopK, Vespa allows you to run actual machine learning models like ONX or XGBoost inside the database to re-rank the results after the initial vector search. The most powerful for complex ranking, जैसे ठीक है, तो मतलब जैसे आपको कुछ कॉम्प्लेक्स रैंकिंग या कुछ करना है, एवरीथिंग यू वांट टू डू इन अ डेटाबेस इटसेल्फ, दैट वेक्टर डेटाबेस, यू डोंट हैव टू क्रिएट सेपरेट लेयर्स फॉर ईच ऑफ दीज, यू कैन डू ऑल ऑफ दीज इन डेटाबेस इटसेल्फ. बाकी जो अदर फीचर्स होते हैं, राइट, टिपिकली कंसिस्टेंसी, ड्यूरेबिलिटी, शार्डिंग, which vector databases support, right? So of course this is again a eventually consistent design. So you take the user request and then you go and update the indexes later, right? So when you insert a vector, it might take a few seconds to index before it shows up in the search result, right? So typically it will also be an eventually consistent design, because I think you cannot support strong consistency here. They use a write, so maybe they will be using wall, and wall is used, Vespa also uses wall. So wall is basically used to support durability. We will say that, okay, I got the user request, but I have not updated the index yet, because it will take it, if I wait on the user thread itself and go and update the index, the user will have to wait a very longer time, and then I'll have to scale a lot to support that kind of use case. So I'll just use a wall for durability. So I have taken an in-memory request, and then I've also updated wall just for, let's say, if the pod restarts or box restarts or VM restarts, then I will use wall for durability. And then this is where I can look back. Then I can, let's say, if a box restart ho gaya, so I can always go to wall, and whatever the last checkpoint I would have stored, after that checkpoint, I look back, and then I can create my in-memory index by looking at wall, right? Sharding typically up. So different databases will use different kinds of ways to do the sharding. So जैसे Vespa में there is this is a bucketization which it uses. So there is a concept of virtual buckets like Redis or Cassandra has, right? Where we say कि आपका जो भी document ID है, you will convert it to you will pass it to a hash function, and then hash function will give you one bucket, and then all that document will go and logically get stored on that bucket, right? So logical separation देता है. So let's say now you have to move documents from one content node to another content node, the entire bucket moves instead of that particular that document by document movement नहीं होता, पूरा bucket by bucket movement होता है. So that's how now I can say, let's say अगर मेरा 1 million documents है, right? And then 1 million documents gives me a footprint of I need 32 GB of RAM, right? So what I can do is I can store all my documents on, let's say, 3 nodes or 5 nodes or 10 nodes, but it's a replica based setup. It's not a sharded setup. So there is no sharding. All my content nodes are hosting the exactly same nodes, right? So this helps me very easily. I can do a read scale up. So read karna hai. So read mein I don't need to do a scatter gather at this layer. I will just pass on the request to any of the content nodes. I can take the result and then return it to the user. But and then so this helped me scale my reads a lot, right? But let's say आपको write जो है, write आपको you'll have to still go and do on all the nodes. So Vespa में you can tune that write. I will wait for, let's say, 2 nodes or 3 nodes to accept that write and then acknowledge, and then other nodes which may make they can receive the nodes the upwrites from the other nodes, right? This is very similar to like a peer-to-peer database like Cassandra is, right? So Cassandra is very similar to, in that aspect, is similar to how Cassandra does the writing. Yeah. And then one is the recent thing is the hybrid evaluation. So what I have come to understand is that now vector will just become like one more index in the same existing databases, right? So we've already seen that Solar also supports HNSW index, Elasticsearch also supports, OpenSearch also supports HNSW index. So even the existing data, in fact MongoDB also supports, and Postgres also supports HNSW index. So what will become is that these databases will, instead of vector it being like a separate database for vector search, the existing database itself will start supporting HNSW index and will become like a hybrid database where you do lexical search also and then you do a vector search also, right? And similarly, so Vespa is already, it was a lexical search earlier, you've seen, but they have started supporting HNSW index. So similarly, you will see that this kind of a trend is becoming more and more this. So maybe in organization, this is, and we can take a choice that whether we have to go with a separate vector database purely. I think we connect. I think I think companies does not do it. Usually they see that can we do this in our existing document-based stores itself, and we can use it for vector use cases also. Maybe we'll have a different cluster, purely different cluster for vector and purely different for lexical, and then we will merge the result, right? So you search both the data source in parallel, then merge the result, and then for vector search you will use some kind of a layer which does helps you do a pruning to say that okay, your vector's result Aya, is that good enough or not, because vector will always give you the result, right? It will never say no. So some kind of a pruning or Q2P layers are put on top of vectors to do the pruning. So this is, uh, and then you can, let's say, you can do a full text search also, and then you can do a vector search also when you have this kind of a setup inside the same database. So so there is a top K problem that you will not have this top K problem when you do this both, right? Yeah, I think this is all I had. Any questions?
I think good one.
Yeah, this is good.
ठीक है, मैं डॉक्यूमेंट शेयर कर दूंगा. Any question, Brijesh?
नहीं नहीं, ये आई थिंक आउट ऑफ ऑल दिस सेशंस ये कॉम्प्लेक्स था. कभी मैंने एक्सप्लोर नहीं किया कभी ना, तो
हाँ, ये कॉम्प्लेक्स तो है. इसमें मुझे भी अभी ये इंडेक्सेस के बारे में और क्लियर करना है, और वेक्टर डेटाबेसेस आल्सो. आई थिंक वेक्टर डेटाबेस में तो मुझे बहुत कुछ अलग नहीं मिल रहा है. अब थोड़ा सा ट्यूनिंग डिफरेंस है इन इंडेक्सेस वगैरह का, बट देयर इज नॉट मच मोर इनटू दोस.
Yeah, the fascinating thing is like they support like 10 billion vectors, right? One more than that. I mean, you can scale accordingly, but I mean, searching and those things. And yeah.
हाँ धीरज, कुछ कह रहे थे?
No, that's something. It's good, man.
nothing recording, you can stop.
Recording.
Okay.